Okay, let's continue. We will talk about module 2, chapter 2 today, which is full of unsupervised learning. I'll try to finish this in a single video because this is kind of an easy chapter and not too much of complexities are there. What we are going to primarily talk about is clustering techniques, and we are mostly going to talk about k-means clustering, and then we'll talk about a little bit about say hierarchical clustering, and then we'll also going to have a very minimal small reading on density based clustering. But this chapter is going to talk about clustering at large and unsupervised learning. So as we already know, unsupervised learning happens when your data points, they are not labeled. So what we can do out of this kind of information or this kind of a data is that we can try to find out patterns which puts similar data into similar buckets, and this is what is being referred to as clustering in your machine learning world. So let's start with the most basic or the most easiest form of clustering, or the clustering which is being used most rapidly and easy to interpret, which is called k-means. So what happens in k-means is that and just for interpretability, let's think that there are only two features, because then it is easy to put it in a two-dimensional graph. So let's suppose these are your data points. So intuitively you can understand that this is one cluster, this is one cluster, and this is one cluster. So what happens in k-means is that you pick up random points, random k points, because you want to find out k number of clusters. So you pick up k points. How do you find the value of k? We'll figure out that later, but let's assume that in this particular case k was 3. So you picked up 3 points, and then you find you iterate all other points one by one and see which k point, or let's call these k points as your core points. Okay, so and see which core point is nearest, and if you are fortunate and you have selected one from here, one from here, and one from here, then in the first go itself you'll find out that this will become like one group, this will become like second group, and this will become like third group. So once you have grouped all of these points together, then you find the centroid of each cluster. And then you repeat, and you keep repeating till the time your clusters do not change. And once you reach that kind of an equilibrium, you find out the clusters. So let's suppose your 3 points were these 3 points initially. Instead of, you were not so lucky, so you found out first point this and this as your core points. Then in this case, what will happen is then that probably these points will become part of this cluster. Okay, and these points will probably become part of this cluster, and this will remain as is. But when in your second iteration you'll find the centroids, then this will become the centroid of this cluster, and this will become the centroid of this cluster, and then in the second iteration itself you will be able to isolate these clusters. So so it really doesn't matter so much that how you start, but you will find an equilibrium. Having said that, k-means will give you different results. especially if the value of k is large. So what you have to do is you have to keep trying this many times till the time you feel that your clusters really make sense to the business. So that's how it is. There are few things that we spoke, but we did not get into the depth. One is the distance. How do you find the distance between 2 points? Okay, so let's suppose there is di and dj data points. How do you find the distance between these 2 points? And this is where not just here, in general in statistics you'll find that 2 points, the distance can be found out in a variety of ways. So something which is very, very easy is something called as Manhattan distance. So what happens in Manhattan distance is, and let's assume that, or just for simplicity, that this is x1 and y, but only two dimensions are there. Let's suppose here this is distance d1 and this is d2, and then this is x and this is y. So we are only talking about 2 dimensions, but this can go into as many dimensions as possible. So how do you find the distance between the two? Is you find out the difference between their y coordinates, take the absolute value and find the difference between their x coordinates, and then sum that up. So ideally this is this distance and this distance. So distance 1 and distance 2. So sum of this distance and this distance. Okay, so this is called the Manhattan distance. Sometimes it might be the most right metric for you to find the distance, sometimes it might not be. The second distance is called as Euclidean distance, and we spoke about 2 points here, but you can just you can generalize it by saying that it is your feature I of your first point to feature I of your second point, and then you keep summing that for all the n dimensions that are there. So it can generalize. I just gave you an example in 2 dimensions because that is easy to understand. The second distance is called the Euclidean distance, where instead of just taking the absolute values and summing that, we try to find the difference between their coordinates and we square them, and then we take the under root. So in this particular example, this distance between these 2 points here is going to be the Euclidean distance, and this can be generalized in the sense that if there are n values, then your fi minus fi dash square, and then you take you add all of them together and then you raise to power 1 by 2. So this is how it is. If you want to further generalize this, and let me see what is the name of that distance matrix called, because some of these peculiar questions might be there in the exams. So let me, okay, so it's called as Minkowski distance, and it tries to generalize all of this together by saying that if I take fi and fi dash, I raise this to the power of L, and then I take the Lth under root. This is the generalization of Manhattan distance and Euclidean distance, but for all practical purposes we use Euclidean distance. One more distance metric which is also important to understand is called as cosine similarity. So cosine similarity, let's suppose there are 2 vectors p and q. So you take the dot product of p and q and then you divide by their their values. So that's called the cosine similarity. If we want to further simplify this, P and Q, when you say the dot product is nothing but, you know, Fi and Fi dash, their multiplication, and let me put, you know, a sigma here, and then it can be Fi square under the root, and then sigma here, and Fi dash square sigma. So this is going to give you a cosine similarity of two vectors, very popular. And let's suppose this is C. So this can, the range can come from -1 to 1. That's the range for cosine similarity. And since distance is taken as 1 minus C, which implies that the distance can be, if it is -1, it becomes 2, and if it is 1, it becomes 0. So the range of values for distance using the cosine similarity is 0 to 2. So that's the various measures that we can use for distance metric. I thought it is a good idea to talk about these measures, because whether it is k-means or any other kind of a clustering algorithm, first you need to find out whether your data point, say di and dj, how far they are. So whether you use Manhattan distance, you use cosine similarity, or you use Euclidean distance, you should know what all these distances actually mean. Okay, so that's about the distances. The second point we were talking about is you know, how do you find the value of k? So how do you derive k? And before we talk about deriving the value of k, we need to discuss about how do we find the quality of these clusters. So let's suppose our algorithm has given us clusters. So it has given us one cluster here, one cluster here, and one cluster here, and these are your data points inside this cluster. Okay, so, and then there can be various algorithms that can give you different clusters. So how do you find whether the clusters that have been identified are right or wrong, or good or bad, or, you know? So there are two metrics that are generally used. One is called within cluster sum of squares. So as the name signifies, you know, we need to find out that within each cluster, what is the, how cohesive are these clusters, how near are the points from each other. So for each data point within each cluster, let's suppose we are talking about this. So for all of these data points, we find the distance between, you know, di and dj. Let's suppose we are taking Euclidean distance, and then we sum them, and then we take the square root. So, you know, in case we are taking the Euclidean distance, let's assume that, and for most of the practical purposes, we'll use Euclidean distance as a distance metric in most of our calculations. So that's the within cluster sum of squares. So they'll get some number here. Okay, so we use Euclidean distance as a distance metric here, and we find the within cluster sum of distances, within cluster sum of squares. So we get a number here, let's suppose that is x, we get a number here that is y, and we get a number here that is z. So the within cluster sum of squares for the entire scheme of things is going to be, you know, a total of all of this. Okay, so that's how we'll find the quality of these clusters. So your total is going to be x plus y plus z. So that's the within cluster sum of squares. And then there is one more metric which is used, which is called as between clusters sum of squares. So this tells how far apart the clusters are from each other, because while we want the clusters to be cohesive, we also want the clusters to be far distant from each other. So this is probably an easier thing to calculate. We find out the centroids of each of these clusters, and we find out the difference between the centroids, and then we sum them up, as an Euclidean distance. So these are the two matrices that we generally use to find out how good or how bad the clusters are. Sometimes what we may have to do is that we can also use a ratio which is called as variance ratio criteria, VRC, which is nothing but the ratio of the between clusters sum of the squares and the within clusters sum of squares. And this is also one of the, this combines both of them together to give you an indication of how good or bad these clusters are. Okay, now that we have a fair understanding of these matrices of within cluster sum of squares and between cluster sum of squares, we can talk about how do you find the value of k. So to find the value of k, there are a variety of methods. The first thumb rule is that if you have n points that needs to be clustered, generally you divide n by 2 and take the square root. So you should get a good cohesive clusters. Okay, so that's the rule number 1. But if you want to become more granular and you want to do better analysis, we sometimes what we do is we try to plot the graph between within cluster sum of squares and the value of k, and then we see whether if I take say value of k to 2 or more till it can become k, how is this value changing. And let's suppose it reduces to some time, and then the rate at which it reduces becomes lesser. So this is called the elbow point, and whatever value you can see here, let's suppose it is 5, you pick this value. So that's how in most of the algorithms you'll see that this is how the value of k is discovered. So this graph is called as scree plots, and this is how you find the value of k. Now the GARP also has a small reading on if there is any means to pick up initial values, pick the initial k values so that your clusters are in better quality. So now we know that this is how the value of k needs to be found. So let's suppose k is 5, and you also have a distance metric, let's suppose Euclidean distance. But then how do I pick up these 5 values? Is it purely random, or can I do anything else to make sure that the clusters are better built? So yes, you pick up randomly, that's one strategy. And the other strategy is that after you pick up the first value, which is again random, you find out the other value which is far from first value, and then you find out another one which is probably equidistant from this value. So this is 0.2, this is 0.1, and then 0.4 should be equidistant from all of this. So you can do some kind of strategies to pick up the value of k so that all of those k values are not very, very close to each other. So that's what we want to see. So that brings us to the end of k-means clustering. There can be a little bit of things here and there, little bit, which will be there in your book or in your GARP readings, but it is going to be focused around whatever I have told. Good part about k-means is it is easy to do, it is easy to be interpreted, and doesn't need a lot of complexities. The bad part is that you need to find out the value of k, and whether you do it with plotting or scree plot, or whether you find it by some other means. So that's the biggest disadvantage of k-means. The other disadvantage is also that sometimes it can become non-deterministic, and you can get different clusters by running it n number of times. There is a variant of k-means which is sometimes called as c-means or fuzzy c-means, in which whenever I'm assigning let's suppose there is a data point di. So instead of assigning it to say cluster 1 or cluster 2, whatever we discussed earlier, we either assign it to cluster 1 or cluster 2, wherever this is nearest to, we assign probabilities to these clusters, that 0.2 this belongs to cluster 1 and 0.8 it belongs to cluster 2. So instead of giving hard values to a point that this belongs to a particular cluster only, we put the probabilities of this belonging to a particular cluster, and we can also raise to power these probabilities to a value f, which is the fuzzy value. So this is called as c-means, not used so much, but you should know that this is also one of the variant of k-means clustering. So let's move from k-means to hierarchical clustering. So as the name suggests, in hierarchical clustering, we create a hierarchy of points coming together, or data points coming together to build clusters. So hierarchical clustering can be of two types. One is bottom up and the other one is top down. The bottom up clustering, where you start from the bottom side and then you slowly go towards up, is generally called agglomerative clustering. And the one that goes from the top and then slowly comes down is called divisive. So what happens here is that, let's suppose we can talk about both of these things together, because fundamentally the concept is similar. It's only the way you approach the problem is either top down or bottom up. So if you have, let's suppose there are 10 data points. So in your bottom up clustering, in your first iteration, you think that all my data points d1 to d2 to d10, they are a cluster in itself. Then you find out which of the two clusters are nearest to each other. Okay, and based on that you combine those nearest clusters and you make them as one cluster, and then you keep repeating this. That's on the bottom up. On the top down, it's the other way around. You think that my d1, d2, d3 and d10, all of this is one cluster in itself, and then you divide this into two parts so that your distance metric becomes maximized. Okay, so not sure if I confused you or did you were able to understand. So what we have to do is, so if you have, let's suppose these are your 5 data points, so you create a kind of a matrix which is going to be a triangular matrix only, and you try to find out the distance of each of these points with other points. So obviously, because between d and d1 is 0, between d2 and d2 is 0, and your diagonals will be 0, but between your d1 and d2 there will be some value, d1 and d3 there will be some value, and it will be d1 d4 is the some value, and let's suppose this is how. And since these distances are mostly symmetric, so your d1 and d2 and d1 will also have same value. So these values will be mirror images of each other. So that's how it is. Now and the distance metric can again be Manhattan distance, Euclidean distance, or whatever is good for you. Then we try to find out that in this entire matrix, which is the smallest value. Assume y is the smallest value, and then you say that d1 and d3 needs to be combined and they become your single metric. Now in your second iteration, your d1 d3 will become 1 point, and then you will become d2, and then there will be d4 and d5, and similar. d1 d3 anyway is one cluster, then d2 is here, d4 is here, and d5 is here. And then again you try to find out the distance between these points, and this iteratively will go on and on and all till all these clusters will eventually become a singular cluster. Okay, so if I have to represent this as in another format, so if this is d1 d2 d3 d4 and d5, so if these are my clusters, and we said that d1 and d3, I think it was d1 and d3, yes, they came together first. So this is how we found out that the distance between d and d3, let's suppose this is the distance metric, which was only say one distance apart, and this is distance. So these came first, and then let's suppose in your second iteration you found d4 and d5 were together, and then you found that d1 is more close to d4 and d5, or your centroid, and eventually you combined all of this together and it became a singular cluster. Now you create some kind of a threshold where you say that okay, let the distance, I want to make sure that the distance metric is not more than 3, and then you take this as a threshold and you cut this like this, and then you find out that you have, if I cut this from here, this is one cluster, d1 and d3 is second cluster, and d2 is third cluster. So that's how this entire thing revolves. One important thing to note down in these kinds of calculations is that when clusters come together, let's, in case this d1 and d3 was one cluster, and let's suppose this is d4 and d5 and this is d2. Now if I have to find the distance of this cluster with these clusters, how do I calculate? Should I do d4 or d5? So there are two methods. Again, there are multiple methods, but the GARP only talks about two methods. One is called as simple linkage, and the other is called as complete linkage. So in simple linkage, you find out the distance between nearest points. So if d4 is here and d5 is here, you pick d4 in simple linkage. In complete linkage, you find out the distance between the far points. So that's how these two linkages are there, based on which you can find out. So what happens, let's suppose when your d1 and d3 will need to be, when I need to find the distance of d1 d3 to d2 and d4 and d5, if it is a simple linkage, I'll find out which of the two, d1 and d3, is nearest to d2 and d4 and d5. If it is complete linkage, I'll find out which of these two is furthest from these points. So there you can practice a couple of problems around it, which can be, so you can practice a couple of problems around it, which is a part of the curriculum as well. GARP readings, there will be some sample questions in the end of the chapter. You can do that, but I think conceptually, if you can understand this much, it is more than enough, and everything else is just a practical theory. So theory I have told you, otherwise it is just the more you practice, the better you will become. And the last thing in this chapter is density based clustering. Density based clustering. Now what we have seen is that if your if your clusters are like this, these are your data points, okay, or if your clusters are like this, or and there is another cluster which is here. So in these kinds of clustering scenarios, your methods like k-means or agglomerative clustering, etc., may sometimes not give you the right clusters. So you need to find a density based method so that you can say that this outside one is one cluster and this inside one is one cluster. So for scenarios like this, or when your clusters are not circular or in a particular pattern, then also your k-means and other clustering algorithm can give you problems. So to address these kinds of issues, we get into density based clustering. One of the very popular density based clustering method is called as dbScan, where we what we do is we take up two hyperparameters. So one is called the threshold value, and the second one is the count. I'll tell you what this means. Okay, so so there are two hyperparameters, threshold value and count. The threshold value tells us the so let's suppose there is a point P and there is a point Q, and the distance between them is some value, say X. So threshold value gives us an kind of an hyperparameter that if this X value is less than the threshold value, which means that these are in the vicinity of threshold, then you need to call them as a core point. And the count also gives me an indication that a minimum of, let's suppose there has to be a minimum of C points within the threshold distance to call them as a core point. So if let's suppose if the value of count is 5 and if there are 5 points which are within the threshold distance of each other, then all of them become the core points. And if the values are within the threshold distance but they don't reach a prescribed core point, then they are called as border point. And so these are the only two hyperparameters, which is a good part of density based algorithms. And if in such a scenario, what happens if there are, let's suppose, clusters in particular shape or sizes which are this, and let's suppose there are some points here. So in this particular case, what will happen is that these all will become core points. These all will also become core points, and this will also become core points. So there you will find that you don't need a value of k. So you'll see that okay, these are core points, so they become one cluster. These are core points, they become one cluster. This also becomes one cluster. If the points are like this isolated, they become border points, and these are more like anomalies or isolated places which can be ignored. So this algorithm helps you to work with data which has anomalies, which is what is not that clean. So that's where dbScan, etc. algorithms are used. So that brings us to the end of this reading, and we spoke about basically clustering, 3 different forms of clustering, k-means. Then we talk about hierarchical clustering, which can be bottom up or top down, and then we also talked about density based clustering. You should practice a couple of working examples on these clusterings, and this chapter should not be too difficult to get through. Thank you.